Hello, and today we'll be talking about some physics topics. So let's get going. Firstly, we're going to talk about forces, acceleration, and Newton's laws using PET Colorado simulators. So let's use the first simulator about net force. In this case, net force is the result of adding all the forces acting on an object. We do this by adding, let me change that, by adding forces on x and on the y axis to get the resulting vector. So let's visualize this. We have this card, and we're going to select these two little men pulling. In this case, you can see that both men are the same height, more or less the same weight, so they are going to exercise the same force on opposite directions. So we want to get the net force, we're going to add both forces. In this case, they would have to be one adding and one subtracting. We usually tend to see forces pointing to the right as positive, forces pointing to the left as negative. And in this case, it's just going to get simplified into zero because one is pulling one direction, one is pulling in the other direction, and in the end they have the same magnitude, so we're going to have a zero net force. But what happens if I let go? I only have one force in one direction. Minus 50 plus zero is minus 50, so it's only moving on that axis. We can also try to see how, for example, in this case, we can see the sum of forces displayed right here as 50 newtons because we have to subtract from the one of the right the value of the left. And you can see how it's beginning to speed up, how it's beginning to accelerate a little bit. And there we go. Of course, always the bigger man is going to win, or in this case, whatever combination is bigger, perhaps more. No? In this case, we have 150 newtons here, 100 newtons on the other side. So if we subtract them, we get 50 newtons pointing to the right as our net force. Let's keep going. How about we use our second simulator? In this case, we're going to talk about movement. And we first need to do a quick review of the three laws of Newton. Our first law states that a body at motion remains at motion, a body at rest remains at rest unless they are acted on by a force. Our second law states that force is equal to mass times acceleration. And third, for every action there is a reaction equal but opposite in direction. Equal in magnitude, opposite in direction. So let's check this with our other simulator. In this case, no force is being applied, so the card isn't moving. No force, the card isn't moving. Why? Because it wants to remain at rest. This is also what we call inertia. Let's begin adding some force. You can see that it's beginning to speed up. The object is moving because we are now acting with a force onto that object. But what happens if I increase the mass? You can see that it is resisting a little bit more. Let's add even more mass. Curious, it's still moving. It shouldn't do that. Let's try adding values and the masses. Let's displace those as well. And there we go. So let's begin by pushing. You can see that now it's really hard for the man to push. Why? Because we're increasing the mass. In this case, the first law that talks about inertia depends on the mass. The bigger the mass of the objects, the more inertia it's going to have. That's why it's more difficult to push a heavier object than a lighter one, because a heavier object has more mass. It's going to try not to move or try to keep moving a little bit more. Also, what happens if, for example, I increase this and then I let the man go? You can see that the object is trying to keep on with the current state of motion. In this case, it tries to keep moving, and in this case that there is no friction, it will keep moving infinitely, thus proving true the first law of Newton. Let's talk about our second law of Newton. We're going to talk about friction and then acceleration. So first let's go with friction. There we go, friction. So what is friction? Friction is this force that's generated contrary to your movement because of the contact between surfaces. You can see a little bit here that there's a rough surface, and thus no matter how hard I try to push, at first the object is not going to move. And even if I let go, the friction is going to start stopping the object. It won't be able to accelerate any further. We can also again play with increasing the values of the masses. We can display our sum of forces, and let's begin adding force. You can see that it's not moving, still not moving. You can see that the friction force is equal to the applied force, so it won't move. But if we just go over it by a little bit, there we go. We're going to overcome it. How do we calculate this friction force? We take the weight of the object, which in this case would be 50 plus 50 kilograms, times 9.81, which is the magnitude of gravity, and we multiply it by a certain friction coefficient. I can modify that coefficient in here. I can increase by a lot the friction, and you're going to see, you can see how the speed is decreasing. But if I click on no, the object is going to keep moving eternally, always with the same speed. So, we are now learning about friction. We are learning that this is this force that's contrary to movement, and that it's going to be pushing contrary to the direction in which I am trying to move. We have two types of coefficients when calculated friction. We have a static and we have a kinetic. In this case, we have a static friction coefficient. Let me get the man again. In here, we are looking at a static friction coefficient because the object is not moving. We are trying to overcome that friction. Once I begin to overcome it, let me refresh it again. There we go, and we start adding force. Once I overcome the initial static friction, I have to use another coefficient, a dynamic friction coefficient, to calculate the new friction that is going to constantly be pushing against me. How does this relate with the laws of Newton? Well, firstly, we know that for every action, there is a reaction equal and opposite. No? In this case, the friction coefficient gets calculated by the weight, and we use the weight and the normal force. In cases in which we don't have like a string pulling the object upwards, our normal force is going to be exactly the same as the weight. That's why we can use weight to calculate friction. But if we were to have like a string hanging right there, we wouldn't have to use the weight. We would have to get the effect of the string pushing upwards, and we would have to extract the remaining normal force, and we multiply that by our friction coefficient, and we get our friction. So I hope everything's going fine up to this point. I hope we are learning a little bit more about friction and forces. Now, as you can see, force is equal to mass and acceleration. What does this mean? That the more I increase the mass or the more I increase the acceleration, and we're going to see that with our fourth simulator, the more my force is going to increase. Also, for example, if I solve for acceleration, the bigger the force, the bigger the acceleration. If I increase the mass, it's going to have a lower acceleration in this case. Let's do some examples. Let's go over here to my acceleration one. Where do I have that one? That's a good question. If I'm not mistaken, it should be right here. Applied for this one is friction, this one is friction as well. Acceleration, there we go. This one is one for acceleration. So, if I suddenly add more weight, it's going to slow down a little bit more. If I reduce the weight, the speed is going to increase. We can observe that relationship between mass and forces. You can also see that in this case, the bigger I want the force, the bigger the acceleration. Wait a moment. There we go. The bigger my force, the bigger the acceleration. You can also see, again, our first topic about the sum of forces. You can see that once I remove the force that was pushing, I only have friction going to one side, which is going to de-accelerate. I'm going to have a negative acceleration. That's going to constantly be subtracting from the initial speed I have, until eventually we reach an equilibrium point, and that equilibrium comes at 0. We can also have an equilibrium in which the net forces add up to 0 when we are moving at a constant speed. And our last law of Newton states that for every action there is a reaction equal and opposite in magnitude, and opposite in direction, but the same in magnitude. What do we mean by this? For example, in this case, I'm pushing the object in one direction, and the object is also going to push me into the opposite direction, but with the same force. To some extent, you could say that it happens a little bit the same with friction, which isn't entirely true, because friction isn't the opposite reaction of me applying a force to it. Friction is a constant that stays there. Whether I'm moving or not, there is going to be a friction with the surface. But for example, the weight I exert on a table and the normal force of the table pushing me upwards, that, for instance, is an example of that relationship, of that third law of Newton, as long as I do not have another component on the system, like a string, for example. Because when I add a string, I have another reference, I have other forces pointing to some place or to some other place. I like to think of this example as if you had two cars and you have a bochito and a big truck. If the bochito suddenly runs and pushes the big truck, the one that gets smashed is the bochito. Not because it had less force applying on the truck, because in the end both objects hit each other with the same force, but because of the mass, one object has to feel a bigger effect on the force because it has less inertia. The truck has a bigger mass, has a bigger inertia, thus it isn't as affected as the bochito, which gets squeezed. And that is a little bit about acceleration, friction, motion, and sum of forces. I hope you like this video, so stay tuned for the next one. See you.